Hello, class. Welcome back. Today we are talking about series some more. So we're just going to do some examples to follow up on yesterday. That's just to get better with what we learned about because it is complicated and students have a lot of trouble on this stuff. So just to remind you, last time we defined what it means for this to converge or diverge, and this is called a series. So this thing converges if you take the limit of the partial sums and that just becomes a number. So again, very, very common mistake. You don't just take the limit of this. This would just be the limit of the series. If you were doing, of the sequence, if you were doing a sequence problem. This is the kth partial sum, which sort of takes some work to create before you can take this limit. So our example was that we were able to do was this one. So the partial sums, the kth partial sum turned out to be something like this, I believe. And so that's what we took the limit of, not this, right? This would just go to 0 if I took the limit of just that, but that would be the limit of the sequence. The limit of this tells you the series, and then that turned out to be 2. And that was why we would say that this thing equals 2, okay? Because the limit of the kth partial sums was 2. Okay. So yeah, it's easy to get mixed up with all this series and sequence stuff. So try not to do that. It helps if you just use notation correctly and don't just write random notation for whatever you're feeling, I guess. But that happens too. Okay, so let's do another example. So we are going to show that the harmonic series, which is a very classic example, the harmonic series is the infinite sum from 1 to infinity of 1 over n. So what does this look like? It looks like 1 over 1 plus 1 over 2 plus 1 over 3 plus blah, blah, blah. So the idea is that this one converged. So it is possible to add up infinitely many things and get a finite number. This one is going to turn out to diverge. So show this guy diverges. So what's the difference? The difference is the terms that you add up, they really need to get very small very quickly. Otherwise, you're going to be adding up stuff that's too big and it's going to go to infinity. Here, these things get very small very quickly. And so that's basically why it adds up to 2. So as you go down the sum, so you get 1 over 1 plus 1 over 2 plus 1 over 4 plus 1 over 8 plus 1 over 16 and so on. Those numbers get very small very quickly. These ones will not get small enough fast enough. And that's really the difference in a conceptual way. But we actually have to figure out the partial sums to do this. So let's do it. Okay. So we need to know information about the partial sums. So it's best to just start with S1. So S1 is just adding up the first term up to A1, I mean. So I think in the last video I misspoke and I said like you add up this many terms, like 1. But it actually means you go up to A subscript whatever term. So you go up to A1. So in that case, this is just 1 over 1, which is 1. S2 means add up to A2, which in this case would be 1 over 1 plus 1 over 2. So S3, so now you can sort of see the pattern, would be 1 plus 1 over 2 plus 1 over 3. And so SK would be 1 plus 1 over 2 plus 1 over 3, all the way up until you get to K, 1 over K. Now this is actually not helpful yet. What you really need is an explicit formula for SK, like we had for SK in this problem. I'll keep referring back to it. We had an explicit formula here. That's something you can take the limit of as k goes to infinity, but this you cannot. You need a general form. So different problems require different methods for finding this thing. Sometimes it's too hard, which is why we'll learn some other stuff later. But in this one, it's sort of weird. Okay, but first let me see what we're gonna do. So then what should happen is once we have this explicit formula for SK, this limit should be infinity because, or it should not exist because we're trying to show that the harmonic series diverges. If it was going to converge, then this would just be a number in the end. Okay, so I'm going to even call this a proof because it's sort of difficult. So what we're going to do is we're not actually going to figure out a formula for SK, so I lied. What we're going to do is find something that SK is bigger than, which is easier to deal with. So I've got to write out the first 4 terms again just to see the thing that I'm trying to do. Let's do that. So what I want you to notice is, okay, we got to remember fractions. So what's bigger, a third or a fourth? So a third is bigger than a fourth. So that means that if I do a third plus a fourth, that's going to be bigger than a fourth plus a fourth. I hope that is okay with you. So what can I say using that about S4? So S4 has that 1/3 plus 1/4, but as we just said, a third plus a fourth is bigger than a fourth plus a fourth. So if I replace these with that, it'll be bigger than the replacement. So if I say a fourth plus a fourth instead, then it's true that the left side is bigger. And what I'm doing here is I'm going to figure out something about SK using a comparison. So then what I want to do is write this as 1 plus, okay, so this, what's a fourth plus a fourth? That's a half. So this is actually 1 plus, I want to think about it as 2 halves. Okay, this is the pattern we're going to establish for all of the powers of 2. Okay, so the next power of 2 is 8. So that was S4. Now we're going to look at S8. So let me just summarize. S4 is definitely bigger than 1 plus 2 halves. And now we're going to say something about S8. So S8 is 1 plus a half plus a third plus a fourth, all the way down until you get to an eighth. And we're going to pull the same sort of trick here. So this guy, so the first two we leave the same again. But this guy, we're going to say, well, that's bigger than a fourth plus a fourth. But then these ones here, we're going to do something similar. 1/5 is going to be bigger than an eighth, and so is 1/6, and so is 1/7. So if I replace those three with 1/8, then the left side will be bigger than the replaced side. So 1/8 plus 1/8 plus 1/8 plus 1/8 is replacing the last four terms. And then we can rewrite this like before. So this is really a 1 plus a half. Those two 1/4 add up to a half. And now the 4 1/8 also add up to a half. So this is really 1 plus 3 1/2. So we're doing a very interesting trick. So to summarize, we have S4 is bigger than 1 plus 2 1/2. S8 is bigger than 1 plus 3 1/2. So what's the next one going to be? If I do the same idea, S16 is the next power of 2 is going to be bigger than 1 plus 4 1/2. So SK is going to be bigger than 1 plus. So it's a bit tricky because this 16 is not the same as this 4, but they are related. And this 8 is not the same as this 3. And this 4 is not the same as this 2. But what's going on is that it's just powers of 2. So 2 to the 4th gives you 16, right? 2, 4, 8, 16. 2 to the 3rd gives you 8, and 2 squared gives you 4. So I actually don't have a formula for SK unless K is a power of 2. So these are different Ks. But I can only do it if it's a power of 2. So I'm just going to change K to a power of 2, 2 to the I, or whatever letter you want, because then an I is what goes here. So we didn't find a formula for all SKs, but we found that SK is bigger than something for K equal to powers of 2. Is the idea. So then we're just going to take the limit of those ones because the other ones, they sort of come along with for the ride. So then the limit as K goes to infinity of SK is what we're normally going to do, but that's going to go the same place as the limit of just the powers of 2. So we're going to do these ones, 2 to the I is the power of 2s. So we can do this limit because that limit has to be bigger than, because of this limit. So the s subscript 2 to the i's, which are really just some of the sk's, some of the partial sums, just the powers of 2 ones. Those are all bigger than 1 plus I times 1/2. And now this limit I can just do. So what's the limit of 1? Well, it's just 1. But what's the limit as I goes to infinity of, this is really just I over 2. Well, the variable that's growing to infinity is on top. So it just grows and grows and grows to infinity, and so we get infinity. So what we've shown in a very roundabout way, without actually ever knowing the partial sums, is that the limit of the partial sums will be infinity, because we do know that they'll be bigger than something that goes to infinity. So that's the idea. So we show sk is bigger. We never actually get a formula for sk. We just show a formula that it's bigger than. So we show that sk is bigger than something going to infinity. So it must also go to infinity. So it's sort of just a comparison. Okay, and this is a very powerful technique, and it's much more possible than trying to actually figure out a formula for the SKs for these things way up here. Figuring out an explicit formula for these things is very hard, but figuring out an explicit formula for what it's bigger than is not as hard. And so that's what we did here. We found this explicit formula for something that it's bigger than instead of for what it is. Okay, so again, by definition, this means that we're done. This thing diverges. Again, because the definition of diverging is that this limit of partial sums goes to infinity. Okay, so that is a very challenging problem, but it displays a good technique and also the need for learning more techniques later that will simplify things. But for now, we're going to do a couple more examples similar to this one. Okay, so here is the next one. Let's look at this one. This one will work very similarly to the harmonic series. So this guy, I'll just tell you, I'll give away the spoilers. It's going to diverge, but sometimes I'll just say like, show it does something or something, and you have to figure out which one it does. Okay, so partial sums. You got to deal with the partial sums because we don't have any other techniques yet. So this is going to be 1 over 2 because it's just the A1 term. In fact, let me just for practice, let's change this actually to a 0. So then S1 means do A0 plus A1, which is what I should have said last time in the previous video, but I messed up. So I'm trying to fix it here. So plug in 0, plug in 1, and it turns out to be the same. Doesn't matter in this case, but that's that 1/2. Okay, so then S2 is 1/2 plus, because it's always the previous one, plus the next term, plus 2 over 3. S3 would be 1/2 plus 2/3 plus the next one would be 3 over 4, and so on like that. Okay, so again, the idea is it's going to diverge because although we are adding fractions, the fractions are not getting smaller in this case. So not only are they not getting small fast enough, they're not even getting smaller. In fact, this is bigger than this. 3/4 is bigger than 2/3. And the more terms you add, you're actually adding bigger terms. Okay, so it's definitely going to diverge. So what can we do? So let's see. Let's try to figure out a pattern that's simpler than these, because it will actually be hard to figure this out. It'll be hard to determine that. So an explicit formula for that. So we're gonna cheat again by thinking about size. So for example, 2/3 is bigger than 1/2. In fact, so is 3/4. So is the next one. They're all going to be bigger than 1/2. So what I can do is I could say, okay, well, S1 is 1/2, but S2, 1/2 plus 2/3 is bigger than 1/2 plus 1/2, which that has a nice explicit formula. It's 2 1/2. S3 is 1/2 plus 2/3 plus 3/4 is bigger than 1/2 plus 1/2 plus 1/2, which is 3 1/2. And S4, for the same reason, okay, I can now start skipping little steps. S4 is going to be bigger than 4 1/2 for the exact same reason as the previous ones worked, and S5 will be bigger than 5 1/2. So now I can say something about SK with a nice explicit formula. It's going to be bigger than K 1/2, because that's the pattern we established. S blank is bigger than that many 1/2. And so then we can take the limit as k goes to infinity of not sk, we can't really do that, but we can say that it's going to be bigger than the limit that we can do, because sk is bigger than k times 1/2. And again, here, k is just growing and growing and growing to infinity. So you have a giant number over 2 that dividing by 2 doesn't matter, it just continues to increase forever. This is infinity. So the limit that we're trying to figure out is bigger than infinity. So of course it has to also be infinity. There's no other possibility for it. And so that means that the series diverges. I started at 0 this time. And I just really want to note, again, the series diverges, and that's different from the sequence. So they don't have to do the same thing. The sequence, if I just look at this sequence, that will actually converge to 1. The difference is the sequence is just where is the list of numbers heading. The series is what are they adding up to. And here they add up to be too big, so they go to infinity and they diverge. But as a list of just numbers as a list, they go towards 1. And that's because you just do this quick limit here, and you're not dealing with the partial sums, and that just becomes 1. Using whatever rule. You can use L'Hopital's or whatever you want, but that'll be 1. Okay, so again, different from the series, which diverges. Okay, same thing for the harmonic series that we did first. So this diverges, but the series certainly converges. I mean, the sequence, that converges to 0, because the list as a list not as a sum. If you're asking where's the list heading, it's heading towards 0. But when you try to add them up, it does not head towards anything. It just grows and grows and grows. But for this guy, they both converged. This one converges to 2, while the sequence converges to 0. Okay, so that was the first example we did. So lots of different types of things can happen, so you got to be aware. Okay, let's do another example here. So this one will also diverge. It's a bit weird. So let's look at the partial sum. So what's S1? S1 would just be -1 to the 1, which is -1. S2 would be -1 to the 1, aka the previous term, plus -1 squared. But what happens when you square -1? It becomes +1 and you get 0. So S3 is just going to be the previous one plus the next one. So I'll just put that 0 there that we already figured out. And then that -1 to the third becomes -1. So you get 0 plus -1 is -1. And then S4 is -1 plus the next one. But that's going to be -1 plus 1, which is back to 0. So SK, we don't really have a formula for, but it's going to be one of two things. It's either going to be -1 or it's going to be 0, because that's what the sequence is doing. So a formula for it is sort of annoying to write. You could write like a piecewise function or something. But you don't need to do that, because what really matters is what SK is going towards, because we need to know this limit of the partial sums to figure out if the series converges or diverges. But we can just look at the sequence that we've created. The sequence of the partial sums, because that's what the limit is really doing, is really saying, where is the sequence of partial sums going? So it starts with -1, then it's 0, then it's -1, then it's 0, and so on like that. And this diverges because it does not head towards anything. It heads towards two things. It doesn't go to infinity, but it doesn't go to a number either. So it still diverges. So that means that this limit, you just say does not exist, instead of saying it's infinity, like in the last one, it still doesn't exist. So because the partial sums don't go anywhere, that means that the series diverges. Okay, so if it doesn't exist, that's another way that the series could diverge. In the last examples, it was because they went to infinity right here. That one went to infinity, and that's why it diverged, the series diverged. But they could also just go nowhere, like the one we just did, and that would be another reason to diverge. Okay, so those are a couple types of tricks that you can use. Let's do one more. So let's see, this one. Okay, so this one, there's not really any trick to it. We're just gonna go for it. So let's find SK and see what happens. So in this case, we can actually get a nice formula for SK. So let's see if we can see the pattern. So S1 is just going to be the first term, 1 over 1 times 2, which is 1/2. S2 is going to be that plus the next one, where I plug in 2 now. So 1 over 2 times 3. So it's 1/2 plus 1/6, which is hard to see if there's a pattern yet. Let's do one more. So 1/2 plus 1/6 plus, now I'm plugging in 3, 1 over 3 times 4. So I get 1/2 plus 1/6 plus 1/12. Okay, so it doesn't look to be like that there's a nice explicit formula that you can plug K into. But if you get common denominators, you actually will. So this is going to turn out to be, let's see, 3 over 6 plus 1 over 6 is 4 over 6, which is really 2/3. And then the next one is going to be, so it's 6 over 12 plus 2. Let's see if I can do fractions on the spot. 2 over 12 plus 1 over 12 is 9 over 12, which reduces to 3 over 4. And we sort of start to see a pattern emerge: 1/2, 2/3, 3/4. Those kind of look like something. And in fact, you could check the next one, but it is going to look like this. So how does S3 relate to 3/4? Well, it's just the same number on the top divided by the same number plus 1. So that's going to be our explicit formula for SK. So in this case, we don't have to say that SK is bigger than something. We can just figure out SK straight up by getting common denominators. And it's hard to know that ahead of time. You just sort of do it and hope you can spot the pattern. Okay, so this time we found, basically, we were able to find this sequence. We were able to find the formula for the sequence. Whereas before, we just knew SK was bigger than something. And we took the limit of that something instead to finish the problem. Whereas here, now we can just do the limit of the SKs, the partial sums. Because we have an explicit formula for it. So K over K plus 1, what does that limit go to? Well, the same power of the variable on top and the bottom, power of 1 for K. So you just get, if you use L'Hopital's rule by changing it to a function or use the shortcut, you end up just getting 1 over 1. And so you get 1. So then that is what the series converges to. The series convergence. So 1 is another way to say it. So again, I just want to emphasize, maybe through this example one more time, that there's a lot of stuff going on. So you're starting off with a series, and then you're creating partial sums, which themselves form a new sequence. And you're trying to figure out what the new sequence converges to, or if it diverges. And whatever it goes to or doesn't go to, that's what the series initially that we started with converges to. Okay, and then in between here, the tough part is always dealing with this stuff and figuring out either a formula for SK, like in this example, or in the previous example, that SK follows this some sort of pattern, which does not converge to anything. And so this limit does not exist. And so the series diverges. Or in the example before that, not touching SK at all, basically, and not ever figuring out a formula for it, but instead figuring out that it's bigger than something with a nice formula, and then taking the limit of that nice thing. And then since SK is bigger than that, the limit is bigger than whatever that limit is. So in this case, it was infinity. So this limit had to be infinity too, which means that the series diverges. Okay, so different types of examples. So that's it for today. I will see you next time.